I'm very glad to be here. I've been basically waiting for this workshop for 2 years now, and for now it hasn't disappointed. Today, I would like to talk about the proper role of linguistically-oriented deep net analysis in linguistic theorizing. I will start with some examples of why I think deep nets should be something exciting to linguists. I will then show that actually, however, this kind of research about the linguistic analysis of deep nets is having basically no impact on linguistics at large. I will argue that that's because we are unclear about the theoretical significance that this work should have for linguistics. And so I will conclude with some implications of my proposal, which is actually the opposite of the one that Roger Levy made yesterday. Namely, I will propose that we should seriously look at deep nets as linguistic theories. When we talk about deep nets for natural language processing today, we are almost always talking of like neural language models that are deep networks that are trained simply by exposing them to a lot of raw text, tuning their weight on the task of predicting the next word. And after they are trained, these networks can be used to generate or to process text. Like all neural networks, these models will map symbolic units to some kind of distributed vector-based representation. But since language unfolds in time, they will need also some kind of device to track information across time. The classic device here is to use a recurrent connection such that at each point in time, the network is fed not only the current input, but also its state at the previous time. And then more recently, other mechanisms have been introduced, such as a sophisticated gating system, such that the network on a unit by unit, on a cell by cell basis, can decide whether to preserve information or to read new information. And very important in the last few years, an attention mechanism such that the network can actually keep a cache of its own representation of the last few tokens and decide when making the current choice to which of these previous tokens to give more weight. So for example, in the toy example here, perhaps if we just heard the cat sat on, the network might decide that cat and sat are the most important previous tokens to decide what to produce next. In this talk, I will often refer to two specific state-of-the-art neural language models, the ones that use the LSTM architecture and the ones that use the transformer architecture. Basically, LSTMs are recurrent neural networks that have a sophisticated gating mechanism, whereas the transformers dispense with recurrent connections altogether and are really heavily based on attention. Now, what is interesting is that these building blocks of these networks don't look at all like the kind of building blocks that we as linguists think are important for grammar, things like, say, syntactic labels and trees. And yet, I think any honest linguist must be amazed by what these networks can do. So, for example, here, I went to the online interface to a pre-trained neural language model, in particular the GP2 model. I just typed as a prompt neural networks despite their dubious past, and the network by itself continued generating, have been the subject of serious and widely disseminated research. For example, the Hinton Institute for Neural Information Processing has produced a series of articles and books that discuss the theoretical aspects of deep neural networks. Now, besides the fact that this is like textually, like semantically coherent, notice that there is quite some sophisticated grammar going on here. For example, I tried to kind of trick the network with a long distance agreement sort of context, neural networks despite their dubious past, but the network correctly continued in the plural form. Or look at this extremely complicated determiner phrase with multiple nestings that the network is producing at the end here. A series of articles and books that discuss the theoretical aspects of deep neural networks. I think that it's very intriguing how good this is. And indeed, in the last few years, a subfield of natural language processing has emerged that focused on analyzing the linguistic performance of deep nets. And one of the most commonly studied phenomena in this domain has been long-distance number agreement. Consider English subject-verb agreement, like in the boy is jumping. What is interesting here is that to determine the number of the verb, like the fact that is in the singular here, what matters is not that boy is the noun immediately preceding is in the linear order of the sentence, but a specific hierarchical structural relation between the head of the noun phrase and the verb, so that in the boy that I saw yesterday with the girls and the dogs on the rocks, still, even if there are 3 plural nouns immediately preceding the verb has to be in singular because of its hierarchical relation with the subject body. So if neural networks which don't have any kind of prior for a hierarchy are getting something like long distance agreement right, it probably means that they are developing some kind of genuine notion of structure sensitivity of linguistic processes. There was a very influential paper by Tal Lintzen and colleagues in 2016, which proposed how to formally study a long-distance agreement with neural networks. What they did is, like, given a pre-trained neural language model, they would feed the model a prefix up to and excluding the agreement element. So, for example, something like the boy that I saw yesterday with the girls and the dogs on the rocks, this was given to the net as context. And then the probability that the network would give to the right and to the wrong continuations, is and are here, was compared. And if the model assigned a higher probability to the right number, we would say that in this case, the model had gotten agreement right. With Cristina Gulordava a few years ago, we ran probably what was the most extended study of long-distance agreement in neural language models. We used LSTM language models, which at the time were the state of the art. They were not trained specifically on the long-distance agreement task. We just fed them lots of text from the Wikipedia, and we found that yes, neural networks actually are pretty good at doing number agreement in a variety of language, English, Hebrew, Italian, and Russian, in a variety of constructions. So, for example, not only subject-verb agreement, but also verb-verb coordination. And most impressively, I think, even when we fed the model nonsense sentences, such as the colorless green ideas that I ate yesterday with the chair sleep and not sleeps, which show that the model are not relying on some kind of superficial lexical heuristics. And at least for Italian, where we tested this, with accuracy that was not really much beyond, it was not significantly below that of human subjects. And similar results were also reported for other common neural language model architecture. So I think this is a very intriguing result. And actually, in the last few years, there has been a lot more cool work on this kind of linguistically oriented deep net analysis. Actually, with Tal Lintzen, we recently published a survey of this area in the annual review of linguistics, if you want to look at it. And by now, there are like annual events where a lot of the papers perform this kind of linguistic analysis of deep nets. There are special tracks at all major NLP conferences. And I would say that most of this work is really like going at the core of the questions of generative linguistics, things about learnability, generalization given insufficient data, the centrality of syntactic structure. So you would expect that like theoretical linguists should be interested in this kind of work. Well, it turns out that this is not really the case. And to give you some concrete examples of this, I went to Google Scholar and I looked at the citations of Tal Lintzen's and colleagues' original paper about long-distance agreement in neural networks. This has been a very influential paper with 486 citations in just 5 years. I went manually through these citations. And what I found is that of 486 papers that cite Tal Linsen's work, the total, including some self-citations, that would like qualify as theoretical linguistics paper is a rather underwhelming number of 3. To put this into context, actually Linsen's paper seems to have had more impact on agricultural studies, where it is cited on work on such linguistically relevant topics as crop classification or winter vegetation quality. You might say that this is because Google Scholar is not very good at tracking linguistics papers. So I also looked at the last issues of 3 high-impact theoretical linguistics journals: Linguistic Inquiry, Natural Language and Linguistic Theory and Syntax. I went manually through the references of the papers that I found there, and I found, and I tried to count citations of DeepNet, of deep learning work there, finding that there were a whopping number of 0. Again, you say maybe I picked the wrong journals here, so I also went to LinkBuzz, which is a popular preprint site for linguists of all kinds. Again, I counted how many of the papers that were on the front page of LinkBuzz on the day in which I did this experiment were citing some kind of deep learning work. And again, the number was 0. So I think that Houston, we are definitely having a problem here, and we need to ask, why should actually theoretical linguists care? We, as linguistically minded NLP people, are very excited about studying the grammatical behavior of deep nets, but what should linguists learn from this work about what they are, theoretical linguists, about what they are interested in, which is the grammatical competence of human beings? Well, or in other words, what is the theoretical significance of deep nets or deep net analysis for linguistics? Well, here, if papers in this area even bother to give a theoretical motivation, it is invariably in terms of this old idea that neural networks are blank slates. And so if a deep net can learn a certain linguistic phenomenon, then it must be that this linguistic phenomenon can just be learned from data without spatial innate knowledge. So for example, I interviewed Tal Linsen about why he thought that his work is theoretically relevant. And what he told me is, well, this sort of simulations can help linguists focus on aspects that truly require explanation in terms of innate constraints. If the simulation shows that there is plenty of data for the learner to acquire a particular phenomenon, maybe there's nothing to explain. And really, if you browse a bit of recent papers in the area, you will very often find variations of this sort of tabula rasa argument. But maybe the classic connectionist networks of the 80s, maybe you could think of them as blank slates, but these modern deep net models, actually, they have like lots of innate building blocks. I already talked about sophisticated gating mechanisms. These are just like hard-coded into the model. The attention functions are hard-coded into the model. Or here you can see a fragment from the popular transformer architecture. And what you see is that actually the units are organized in innate modules, each having a different function. So there is really a lot of innate knowledge here. And more importantly, this results in the fact that different neural networks will behave very differently given exactly the same training data. A beautiful example of this was recently provided by Kharitonov and Chabuni that like trained several state-of-the-art networks on very, very tiny corpora of input-output pairs, corpora that would like radically underspecify what is the right rule to generate the output from the input, so that then at test time, they could see what were the innate preferences that different networks will let emerge. So for example, one of the minimal training corpora they used is the one I'm showing in its entirety on this slide. A goes to B, B goes to A goes to A, B goes to B. This corpus is fully compatible with at least two generalizations, what they call a hierarchical generalization, that is that the output is the symbol that is in the middle of the input, and what they call a linear generalization, which is that the output is the third symbol in the input. Now, at test time, after training the networks on this tiny corpora, on this tiny corpus, Kharitonov and Chabuni would feed a test example, well, a number of test examples that now will disambiguate between the two generalizations. For example, if now we feed the network A, B, A, the hierarchical generalization will predict that the output is B, and the linear generalization that the output is A. And what they found is that actually of four common deep net architectures that are currently used, two showed a very strong preference for hierarchical generalization, and two showed a preference for linear generalization. So the difference here looks quite deep, and I think we can conclude that deep nets are not blank slates. Modern deep nets have complex, highly structured innate architectures, which make them behave very differently when exposed to the same data. Which means to me that, like formal linguistic theories, deep nets are really algorithmic models of linguistic knowledge. So let me a bit elaborate on what you think might be a crazy idea, namely that deep nets should be looked at as linguistic theories. Just like traditional formal linguistic theories, deep nets are actually algorithms that assign some kind of structure to sentences, except that these structures are not syntactic labels and trees. They are rather dense vectors, and the structure building operations, consequently, will rather be equations from linear algebra than, say, discrete tree construction operations. But importantly, just like traditional theories, deep nets can make precise predictions about sentence acceptability. So I think that we should really look at this idea seriously, and to look at it seriously, we need to think about what is missing. And I think there are two important obstacles to overcome here. One is that in the area of NLP, we tend to have a very low commitment to our models. We just like switch from year to year to whatever is the state of the art in applied tasks such as machine translation. So for example, 12 over 13 papers that focused on deep net analysis at the black box NLP event in 2018 were using LSTMs, and then all the papers that did deep net analysis at black box NLP 2020, just 2 years later, were using transformers. And what is interesting is that like none of these 9 papers had some discussion about why there was this big switch between two models that are like very different, no discussion about what kind of linguistic assumptions would be changing here, or even really like engineering motivation. Actually, some of these newer papers would refer to older papers using LSTM as corroborating evidence, without even mentioning that here there has been like a huge difference in the underlying model that is in the underlying theory. So I think we should instead be serious about, if we commit to this model as our linguistic theory, what are the underlying assumptions of it, why they are interesting, how do they influence our empirical results. The second point is, I guess, a more, it's more about kind of like how you do linguistic theory, namely, it is kind of nice to show that our models can account for phenomena that we already understand very well, such as, say, vanilla long-distance agreement. But for a linguistic theory to be interesting, it should also make non-trivial predictions about empirical facts that we don't understand yet. And this is very problematic with deep nets for two reasons. One is that actually trivial changes in the models can make big, qualitatively important differences, which makes it even hard to say what is exactly a prediction made by this model. So as an example of this, recently McCoy and colleagues did a general testing of several models and model variations on the phenomenon of auxiliary fronting in English. I don't want to get into the details here, but you can think of this as basically a natural language version of the difference between hierarchical generalization and linear generalization in the artificial data of Kharitonov and Chabuni that I discussed above. And among other things that they found in this study, I will just directly read from the paper, they found that there was considerable variation across multiple instances of the same architecture that differed only in random seed. The random seeds determined both the initial weights of each model and the order in which training examples were sampled. And so, for example, for one particular model, they found that just based on this random initialization, you could get from the model showing an 83% preference for linear generalization to a 90% preference for hierarchical generalization. You see that this is quite important, right? Because like a big discussion here is like how genuinely sensitive to hierarchy deep nets can be. Well, it turns out that just based on a trivial difference in how the data are presented, the answer can be they are totally sensitive to it or they are not sensitive at all, which makes it hard to say, you know, what are the interesting predictions of this model. Or to give, and the second point is that for the predictions to actually be useful in extending linguistic theory, it's not just enough to say our model predicts this, but we should also have a clear understanding of which components of the model are leading to the prediction. We need a mechanistic understanding of how deep nets process language. And this is something that is very rarely done. Just to give you an idea of the kind of study that I think we should do more of, this is a work that we did in the last few years, led by Yair Lacretz, where we went back to long distance agreement with LSTMs, but this time we did like a very, very granular exploration of the model, going really down to the cell by cell level. And what we found is that actually LSTMs systematically develop a mechanism which is genuinely syntax sensitive, but it is very brittle in that it is characterized by a single flag that is kind of carrying number information between the two elements in the green relation. And this leads to the prediction that when the mechanism, when there are going to be two embedded long distance agreement relations, there is going to be a problem, because this mechanism, when it first encountered the outermost element, the first element of the outermost relation will be recruited by it, and being kind of a single flag, there will be no way for the system to deal with the embedded long distance relation. So in a sentence like the kids that the teacher with the pencils like say, the prediction is that like the relation between kids and say should be easy for the system, but the one between teacher and likes should be difficult. And I think this is an interesting prediction, particularly because actually the relation between teacher and likes is a shorter distance, so perhaps intuitively it should be easier than the one between kids and say. And what we found is that indeed LSTMs behaved in the expected way, but also that human subjects, although to a lesser degree, showed the same asymmetry in finding the innermost relation more difficult to process. I think this is like an interesting result. Notice that it pertains to a single network, LSTMs, a single constructions, and it took us like 4 years to run this study, which is totally not compatible with the kind of pace of development of the field nowadays. So I think if we really want to do this kind of studies, we have a bit of a sociological problem here, because every year just so many new models, so many new phenomena are presented, and maybe we don't stop enough to think about what's going on. So coming to my conclusions, I think that deep nets are exciting for us as linguists, and to make them more relevant to theoretical linguists, we should think of them as linguistic theories. However, to do this, we should stop shooting the moving target of the state-of-the-art performance and rather commit to our models and really spend time understanding these models well at a mechanistic level. I haven't really said anything about how a deep net theory look like. The obvious thing is just to take these big nets at face value and so come up with like something which is a very different form of linguistic theory, one which is based on massively distributed representations. Notice that in the past, this kind of idea was criticized because these models were seen as unopenable black boxes. I think nowadays this argument against this idea are weaker because NLP and machine learning have now developed sophisticated experimental methods to actually probe inside these models. But I think that another interesting alternative will be to actually think of a symbolic theory of language, which, however, is based on primitives inspired by mechanisms such as gates and attention in the transformers and other networks. I think that the most successful attempt ever to combine connectionism and symbolic theories was optimality theory. And what I'm suggesting here is that maybe we should think of something similar, a symbolic theory of language, which is, however, based on the kind of building blocks that are postulated by these neural networks. Now, when I presented an earlier version of this work at a computational linguistics conference earlier this year, the most frequent question I got is like, why should we care? Why should NLP people care about reaching out to theoretical linguists? Well, if you are just interested in NLP applications, to be honest, it's not clear that putting a lot of, having a lot of interaction with linguists will help there. The recent history of the field shows that that might not be the case. But given that there is a large sub-community of NLP people that are really interested in doing this linguistically oriented deep net analysis, I think these people should actually feel frustrated that their work has no impact on linguistics at large. And for theoretical linguists, I think that even if you believe that the big success of deep nets in language-intensive applications such as machine translation is based on some priors that are completely different from the ones that make up human linguistic competence, I think that you should be curious about how such architectures that have nothing to do with human linguistic competence are doing so well at language-intensive tasks, because perhaps that can help us delimiting what is truly unique about human language competence. But I think even more importantly, I see sort of like a complementary role here. Traditional formal theories are very good at sort of precise algebraic aspects of language, like say getting scope relations among quantifiers, recursion in syntax and the like, but they're not so good at the sort of like large scale fuzzy phenomena, such as like all the nuances of lexical semantics, the partial regularities of derivational morphology, the partially lexicalized patterns in syntactic constructions. And perhaps, given that deep nets are good at large scale and fuzzy, here is where really a deep net theory could complement current linguistic theories. And with this, I'm really concluding. Just 10 seconds for advertisement. I was just awarded an ERC advanced grant, and I'm looking for postdocs and PhDs to join my team. So if you're interested, please get in touch with me. Quickly thanking several people that I had discussions with that led to this presentation. And of course, thank you for listening to me.